Hey there, science fans! Today we're diving into the exciting world of thermal power plants. These incredible facilities are like giant kitchens that cook up the electricity we rely on every day. From powering our homes to running our factories, thermal power plants play a vital role in our modern lives. But how do they work? It's all about harnessing the energy stored in fuels like coal, oil, and natural gas. These fuels are burned to create heat, and that heat is used to generate steam. This steam, my friends, is the real powerhouse. Think of it like a tea kettle. When the water boils, the steam pushes out of the spout. In a power plant, that powerful steam spins turbines, which are like giant fans. And as these turbines spin, they power generators that produce the electricity we need. So buckle up, because we're about to take a step-by-step journey through a thermal power plant and explore the amazing science that makes it all possible. Let's start at the beginning with the fuel. Thermal power plants can use different types of fuel, each with its own pros and cons. Coal, oil, and natural gas are the most common. These fuels contain stored chemical energy, just waiting to be released. The first step is combustion, which is a fancy word for burning. The fuel is fed into a giant furnace called a boiler. Inside the boiler, the fuel is burned at extremely high temperatures. This combustion process releases the stored energy in the fuel as heat. Think of it like lighting a match. The matchstick is the fuel, and striking it creates the spark that starts the combustion. In a power plant, the combustion process is carefully controlled to ensure efficient and safe energy release. As the fuel burns, it heats up water that circulates through pipes inside the boiler. This brings us to the next step: steam generation. The boiler is the heart of a thermal power plant. It's a massive steel structure filled with tubes carrying water. Remember that heat from the burning fuel? Well, that heat is transferred to the water inside these tubes. As the water absorbs more and more heat, it starts to boil and turn into steam. This isn't your ordinary kitchen steam, though. The steam in a power plant is superheated and pressurized, which means it carries a tremendous amount of energy. Think of it like pumping up a bicycle tire. The more air you pump in, the higher the pressure inside the tire. Similarly, the steam inside the boiler builds up enormous pressure, ready to unleash its power. This high-pressure steam is the key to generating electricity, as we'll see in the next step. Now let's meet the dynamic duo that transforms steam power into electricity: the turbine and the generator. The high-pressure steam from the boiler is directed towards a turbine. A turbine is a machine with blades mounted on a rotating shaft. When the powerful steam hits these blades, it causes the shaft to spin rapidly. Imagine blowing on a pinwheel and watching it twirl. The principle is similar, but on a much grander scale. The turbine's spinning shaft is connected to a generator. A generator is essentially a giant magnet surrounded by coils of wire. As the turbine spins the magnet inside the generator, it creates a flow of electrons in the wires. And guess what? That flow of electrons is what we call electricity. After the steam has done its job of spinning the turbine, it needs to cool down and return to its liquid form, water. This is where the condenser comes in. The condenser is a large heat exchanger that cools and condenses the steam back into water. Cold water from a nearby source, like a river or lake, is circulated through pipes inside the condenser. The heat from the steam is transferred to the cooling water, causing the steam to condense back into water. This condensed water is then pumped back to the boiler, where it can be heated again to start the cycle all over. But what about that warm, cooling water? It's usually pumped to a cooling tower, a tall structure that resembles a giant chimney. Inside the cooling tower, the warm water is sprayed into the air and cooled through evaporation. The cooled water is then returned to the source, ready to be used again. Section 6. Dealing with the leftovers, ash. Handling in coal plants. Burning coal produces ash, which is the leftover inorganic material. Coal-fired power plants need a way to manage this ash. Ash is collected from various points in the plant, like the bottom of the boiler, and from devices that clean the exhaust gases. This ash is then transported and disposed of safely. Modern coal plants have systems to minimize ash and reduce its environmental impact. It's important to handle the ash responsibly to protect the environment. Section 7. Sending power out. Electricity distribution. Remember that electricity generated by the spinning generator? It's not ready to power your home just yet. The electricity generated in a power plant is typically at a very high voltage. This high voltage electricity is then sent to a transformer, which steps up the voltage even higher. Why? Because high voltage electricity can travel more efficiently over long distances with minimal energy loss. Think of it like sending a package. It's more efficient to send a large truckload of packages to a central distribution center than to deliver each package individually. The high voltage electricity travels through a network of power lines to substations. At the substations, transformers reduce the voltage to lower levels suitable for distribution to homes and businesses. Section 8. Key players. Components of a thermal power plant. Let's review the key components of a thermal power plant. We've got the boiler, where fuel is burned to generate heat. The heat turns water into high-pressure steam. That steam powers the turbine, which spins the generator to create electricity. The condenser cools the steam back into water, and the cooling tower helps cool the water used in the condenser. In coal plants, there's also an ash handling system to deal with the leftover ash, and of course there's the whole electricity distribution system to transport that power to where it's needed. Section 9. Efficiency and the environment. The challenges and solutions. Thermal power plants are essential for meeting our energy needs, but they come with challenges. One challenge is efficiency. No energy conversion process is 100% efficient, and some energy is always lost as heat. Another challenge is environmental impact. Burning fossil fuels releases pollutants into the atmosphere, contributing to air pollution and climate change. However, there are ongoing efforts to make thermal power plants cleaner and more efficient. New technologies are being developed to capture and store carbon dioxide emissions from power plants, preventing them from entering the atmosphere. Additionally, researchers are exploring alternative fuels and renewable energy sources to reduce our reliance on fossil fuels. By improving efficiency and reducing emissions, we can work towards a cleaner and more sustainable energy future.